bonds. So, the first thing to review is molecular polarity, right? So this is kind of going back to the chapter 4 stuff, looking at Lewis structures and bond polarity. So there's two major things that are required in order to have a polar molecule. Do you guys remember what they are?
Asymmetry.
Asymmetry. Which could be lone pairs or different attached atoms. You guys know what I mean by different attached atoms? So if all of the atoms that are attached are not the same thing, that would be an example of an asymmetric molecule. Any questions about asymmetry, what it means, what it looks like? Cool. So what's the other thing?
Polar bonds?
Polar bonds, exactly, right? So we have to have polar bonds. If we don't have polar bonds, it doesn't matter if the molecule is asymmetric because it's still going to be nonpolar, right? Does that make sense? Yes.
Yes.
Cool.
Can you give me one example of what a polar bond looks like?
Yes, absolutely. So polar bond, it's easier to think about what makes nonpolar bonds, right? So these are the guys that aren't ever going to be polar, right? So if you have carbon bonded to hydrogen, nonpolar. Always, right? Anything bonded to itself, themselves, whatever, nonpolar. Right, so an example of this would be any of the diatomics. Right, so what are our diatomics?
Oh, like O2?
Have
Is it the ice cold beer thing?
no fear of ice cold beer, right? So every single one of these guys is just bonded to itself, right? Does that make sense? So there's no difference in electronegativity. Which is what makes a bond polar, right? You have to have a difference in electronegativity. Does anybody remember what electronegativity is? Basically, it doesn't have to be a textbook definition.
I was gonna say like the tendency to pull more electrons.
Yes, totally, exactly. You're killing it. Yeah. No, that's great. So, so some atoms are hungrier than other atoms, right? So, things like nitrogen, oxygen, and fluorine are very electronegative. right? So when they're bonded with other atoms, they don't share very well, right? Meaning that they form very polar bonds, right? Question, Steph?
So anything bonded to nitrogen, oxygen, or fluorine would be essentially polar.
Unless you're talking about these guys.
Okay.
Right?
Got it.
Because here they're bonded to themselves, right? So even though they're very electronegative, when they're bonded with each other, their difference in electronegativity is not anything.
So like water, hydrogen and oxygen.
Exactly.
Electronegative.
Exactly. Right. Yeah. So hydrogen is not very electronegative, meaning it kind of doesn't care if it gets its electrons stolen, right? But oxygen is very electronegative, meaning it really wants those electrons. Okay.
And describe does this like dispersion or
That's exactly where we're going with this. Yes. I love it,
okay,
Steph. Thank you.
It's like different example. Okay.
Yeah. So when we're talking, so this is why I wanted to review this, because it's definitely relevant for the exam, but it also goes into what we're going to be starting this next chapter, which is chapter 8. So we already talked about intermolecular forces, right? But I want to bring it back now to intermolecular forces. So this is kind of chapter 8, right? Because the lead-in from intermolecular forces is talking about how molecules are able to stick to each other, right? So up to this point, a lot of what we've been talking about has been how atoms stick to each other to make molecules, right? AKA bonding between atoms in molecules. What we're going to talk about in chapter 8 is how molecules can stick together using those intermolecular forces, right? So if you have stronger intermolecular forces, right, the molecules are going to be stickier, right? That stickiness between molecules is what gives rise to condensed phases, like liquids and solids, right? Without those attractive forces between molecules, everything would be a gas.
Oh.
Yeah, so that's where we're going with this. Does that make sense? Kind of, sort of? So that's why I want to review the intermolecular forces, go through that, and then we'll talk about how those properties give rise to these condensed phases. So, just so we can define this. Oops, phase. Right, so condensed phases are going to be liquids and solids, right? Non-condensed this one's singular, right? Just a phase, and that's gas.
Okay.
So condensed means stuck together or more tightly packed, whereas a gas is going to be disperse. Right? So that's kind of the language we use around that. So, getting back to our intermolecular forces, right? I don't remember whether we talked about the definition of these, but the intermolecular, inter means between, right? So this is literally between molecules, right? So these are the forces between molecules, as opposed to bonding, which is called an intramolecular force. Molecular. Where intra means within, right? So this is talking about the forces within a molecule, right? The things that are sticking it to itself, or that sticking the atoms together to form the molecules. And this is talking about the interaction between molecules, right? The intermolecular forces. So, we had 3 basic flavors of IMFs. That's these guys. I'm way too lazy to write that out a bunch of times. What were they?
Hydrogen bond, the London dispersion, and help me out, folks. Help me out. I know it. Somewhere.
It's like the one thing that I struggle with for some reason.
Dipole, dipole.
Yeah, that's what I meant.
You got it, it's okay. Okay, so in terms of strength, right, which one is the strongest?
Hydrogen.
Hydrogen bonding, right? So strongest is hydrogen bonds.
Mm-hmm.
And weakest
Is the...
You got it. Dispersion.
Okay.
Dispersion or London, right? Either one.
Yeah.
And then in between there, we have the dipole-dipole. Now, strictly speaking, H bonds are just a type of dipole, right? They're just the strongest type of dipole. So let's talk about what this word means. Right? So a dipole is a net separation of charges in a molecule. Right? So we can talk about a dipole when we're talking about polar bonds, right? But if the molecule is symmetric, then we don't have a net dipole, right? So dipole-dipole interactions can only occur in molecules that have a net dipole on the molecule, right? So this word dipole is really just a fancy way of saying it's polar, right? Does that kind of make sense? Cool. Questions about these so far? Cool. All right. So now let's get into some examples. So for hydrogen bonding, right, there's only 3 atoms that can do hydrogen bonding, right? So obviously the hydrogen in hydrogen bondings is this guy. Sorry, I got lag right now. Hydrogen.
And then it's carbon and oxygen?
Not carbon, not carbon. They don't form polar bonds at all, right? So thinking about a hydrogen bond, right? This is the most polar kind of bond, right? Does that make sense?
Mm-hmm.
Because we're saying that this is a type of dipole-dipole, right? But it's not just a dipole-dipole, it's the strongest kind of dipole-dipole, right? So, what would make a really strongly polar bond?
Hydrogen and oxygen.
Yeah, absolutely. So why would hydrogen and oxygen make a really polar bond?
Oxygen is extremely electronegative.
Yes, exactly, right? Who are the other guys who are really extremely electronegative?
Fluorine.
Mm-hmm.
And
Nitrogen.
Nitrogen, exactly, right? So these are the only 3 bonds, right, that can do hydrogen bonding. And it's not enough to have hydrogen and fluorine in a molecule or hydrogen and nitrogen in a molecule, right? They have to be bonded together. Does that make sense? You guys picking up what I'm laying down? So, for example, I don't know if we had this one on the quiz, right? This is a bad example. Let's do this guy, right? So you may not know this just by looking at it, but the Lewis structure for this guy, sorry, I can do better. I don't know why I started right there. Is going to look like this, right? Mm-hmm. So when you draw this molecule out, are there any oxygen-hydrogen bonds there?
No.
No, right? So it's not just about having hydrogen, oxygen, or nitrogen in a molecule. The oxygen and the hydrogen have to be bonded together, right? So an example where you have that happening, as Steph said, I think, is water, right? So water has oxygen directly bonded to hydrogen, right? That makes this bond very polar, right? And again, it's not enough to have a very polar bond. What else do you need to have in order to have a net dipole? AKA a polar molecule.
A separation in charges?
Yes. So if a dipole is just code for polar molecule, right? What makes a polar molecule?
The electronegative?
So we have the polar bonds. Yep, that's one component, right? But what else do you need in order to have a polar molecule?
You have to have a hydrogen-oxygen together, right? No?
What? You know, do with the lone pairs?
Yeah, exactly. Asymmetry, right? So remember when we were talking at the beginning about the asymmetry in the molecule, right?
Yeah.
So in order to have a dipole, aka a polar molecule, right, we need to have a symmetry, right? Which we have in water. We have these 2 lone pairs, right? That makes it asymmetric. Does that make sense, guys?
Yeah.
So again, when we talk about intermolecular forces, it brings together a lot of the concepts that we've learned in Lewis structures, how things are attached to each other, but then it also brings in this concept of bond and molecular polarity, right? And how those things give rise to interactions between molecules, okay?
You could have more than one intermolecular force happening at a time.
Absolutely. Yeah, absolutely.
I always thought it was like only one. Like
no. Yeah.
One of
So,
three.
yeah. So no, that's not true, right? So everything, all molecules and atoms have dispersion forces.
Oh.
Right? So even water has dispersion forces or London forces, right? But that's not the dominant force in water, right?
Gotcha.
Meaning it's not the strongest intermolecular force, right?
Gotcha.
So I think about it as, you know, you all have things that you're strongest at, right? You know, maybe some people are really good runners. I don't know, something like, I'm just spitballing here, guys. But Yeah, that's fine. That's okay. Some people are really good sandwich eaters. Me, this guy right here. Just because you're good at one thing doesn't mean that that necessarily translates to being good in another thing, right? So you can have this quality of dispersion, but not have it be the thing that defines you as a molecule, right?
Yeah.
Does that make sense?
Yeah.
Oh, this is such a good discussion, you guys. We're getting things. Does anybody have any questions so far? We're okay? Cool.
Professor, do you have any example that you can have hydrogen bonding as well as dipole-dipole?
So that's a great question. So everything has dispersion forces, right? But hydrogen bonding is a type of dipole-dipole. Right? So if you have a hydrogen bond, you absolutely have dipole-dipole. Does that make sense?
Yes.
Just
like even though, like for example, hydrogen bond with chlorine, is that still hydrogen bond?
No.
And dipole-dipole?
Right? These are the only ones that can be hydrogen bonds.
Right. So it had to be fell into those three atoms.
Exactly. Yeah. So you can have, so all hydrogen bonds are dipole-dipoles, right? But not all dipole-dipoles are hydrogen bonds, right? The only dipole-dipoles that are hydrogen bonds are these three.
Okay.
Does that make sense?
Yes.
Such good questions, you guys. I love this. Other questions about what we're looking at here? Awesome. Okay, so when we're looking at this kind of molecular asymmetry that gives us polar molecules, I just want to draw this guy again, right? We know that oxygen is more electronegative, right? So where's the partial negative charge on this molecule?
Oxygen?
Mm-hmm, exactly. We redraw that little delta minus. So then where's the partial positive on this molecule?
The hydrogens?
The hydrogens, exactly. Right? And just to reiterate what we're talking about in this hydrogen bonding is we're saying that these partial negatives and partial positives are so strong because oxygen is so electronegative that the partial negative on this guy is strong enough to attract the partial positive on other water molecule hydrogens, right? That's what gives rise to this hydrogen bonding, right? Cool. And we'll look at some pictures in just a second. I think the pictures are helpful. Any other questions about hydrogen bonds? We're okay. So, next up we have dipole. Dipole, which
Can I
again...
ask a super random question really quick?
Yeah, go ahead.
So covalent bonds are stronger than hydrogen bonds, right? Because hydrogen bonds are kind of, they bond a lot and they're strong, but they can break easily.
So hydrogen bonds, as a term, is actually a misnomer.
Okay.
Yeah. So it's not actually a bond, right? It's called hydrogen bonding because it's the strongest type of force that you can have between molecules, right? Okay. But technically, bonds are strictly defined as the glue that holds atoms together in a molecule, right? So when I think about bonds...
I know, it's digressing. It's
No, this is good. This is really, really good because understanding this is like super important to being able to get the concept of intermolecular forces. So bonds are glue holding atoms together. sorry.
Mm.
In molecules or compounds, right?
Right.
Intermolecular forces are more like Velcro, right? So they're not as strong as glue, right? And we're not talking about sticking atoms together necessarily, right? It could be atoms, but we're really talking about the Velcro that holds molecules, together to form condensed phases.
Kind of like it's just a different purpose in a way.
Exactly. Yeah. Yeah. So it's a misnomer when we talk about hydrogen bonds, right? They're not true bonds, right? So I think that's probably one of the number one most confusing things about this. But they're given this title of bonds because they're so strong, right? They're still about, so hydrogen bonds are about 2 to 5% the strength of covalent bonds.
Okay, well.
Just for
we know.
scale.
When you put it like that.
Right, yeah. No,
I
and I think that relative understanding of the size difference is really important, right? So when you're talking about, so one of the ways when we talk about bond strength, what we're really talking about is how much energy it takes to break a bond, right? So that's what bond strength is talking about. So if we wanted to break up an oxygen molecule, right? How much energy would it take for us to break these guys apart, right? And the more bonds we have, the harder it is to get them apart, right? So double bonds are harder to get apart than single bonds. Triple bonds are harder to get apart than double bonds, right? So strength in bonding is about how much energy it takes to break a bond. When you talk about strength in intermolecular forces, what you're talking about is how to separate molecules in condensed phases. Now, that's a really complicated way of saying, for example, if we have the condensed phase solid, right? And we did something to give these solid molecules more energy, right? What happens when we give a solid more energy? What happens to the solid? Go ahead. What were you saying?
Does it change phase?
Yeah,
like
absolutely, right?
Liquid or,
yes, exactly, right? So when we give energy to a solid, we're giving the energy to break up those things that are sticking the molecules together, right? So that could mean that you go to a liquid, right? If you're in liquid form, and you give it energy, what can you do?
Big gas.
Yeah, you can make it into a gas, right?
It's like so many lights are going off about reactions right now, and like different like combinations of combustion.
Yes.
It's just like clicking a little bit more.
Yes. And this also goes back to a million years ago in the semester when we were talking about physical versus chemical changes, right? So chemical changes have to actually alter the molecular structure, whereas physical changes are just changing some property, right? So these types of phase changes, right, when we go from a solid to a liquid or a liquid to a gas, would be examples of physical change, right? We're not changing the molecules, right? We're just giving them enough energy that they can get away from each other, essentially, right?
Yeah. Cool.
Yeah.
That really helped. Thank you.
Yeah, of course, of course. Other questions here? Good. That was a really, really good question about the hydrogen bonds, because I think that's a really common misconception, because they use the word bond, but it's not actually a bond, right? Coolsies. So, just a reminder, dipole are only present in polar molecules. Right? So, in order to have dipole-dipole interactions, you must have a dipole. In order to have a dipole, you must have a polar molecule, right? So, all hydrogen bonds are dipole-dipole. Not all dipole-dipole are hydrogen bonds. Okay? Questions about that? Excellent. How we doing with this stuff, guys? A little better? Awesome. Any questions? So let's look at an example of a molecule that has a dipole but is not hydrogen bonding. So let's say we have carbon attached to 3 hydrogens and 1 chlorine, right? So now there's no lone pairs on carbon, right? But the asymmetry in the molecule comes from having different attached atoms, right? We know that carbon bonded to hydrogen is going to be nonpolar, right? You guys with me on that? Cool. But carbon bonded to chlorine is going to be polar, right? And because we don't have a chlorine on the other side, right, to offset that polar bond, right, then we have a net dipole in the molecule, right? So on this molecule specifically, where is the partial negative charge going to be? Who's
The chlorine?
Yeah, absolutely. So there's going to be a partial negative here, right?
And it's going to be going towards the hydrogen?
And there's going to be a partial positive on your carbon.
Yeah.
Right? The partial positive on the carbon will also pull a little bit of the electron density off of your hydrogens, right? So it makes the whole base of this molecule kind of partially positive, right? And we'll look at some electron maps of pictures of molecules. I think that'll help you guys understand what we're talking about here a little better. But I just want to talk about dipole-dipole interactions, right? So we know that carbon and chloride bonded to each other will be a polar bond, right? But the strength of the polarity in the bond is much weaker than if we had, say, hydrogen bonded to oxygen, right? This one is stronger. This one is weaker, right? In terms of its polarity. Does that make sense? So, when we're talking about the strength of polarity, we're talking about the separation of charges, right? So a weaker bond polarity means that you have less negative here and less positive here relative to this stronger charge separation, right? Charge separation is what allows you to have molecules attracted to each other, right? So less charge separation, less molecular attraction, right? You guys picking up what I'm laying down?
Mm-hmm.
Cool. So, last but not least, we have dispersion forces. Okay? So, dispersion forces are temporary dipoles caused by electron movement in atoms or molecules. Okay, so what the heck am I talking about? So I'm just going to start off with an atom by itself because this is the easiest way to think about it. So if we have an atom, we have our positively charged nucleus, right? And we got some electrons floating around in here, right? Now, the way that I drew them, they're far apart. Why does that make sense? You're muted, Jessica.
Because they float around.
They float around, but why did I draw them so far apart?
Because they don't like to be near each other?
Yeah, why?
Because they're special?
Because they repel each other, right? So when we talk about opposite charges are attracted to each other, right? But when we talk about same charges repel each other, right? Does that make sense, guys? So these electrons don't want to be near each other, right? So we know that they would be happiest, as it were, when they're farthest apart, okay? But we know that these electrons are not standing still, right? They're always moving around. So electrons are always moving around. Go ahead.
So they're always going to be nonpolar, right?
No.
No. Okay.
No.
I'll be quiet.
No. No. That's okay. So what you're talking about nonpolar is a lack of separation of charges, right?
Mm-hmm.
So what we're saying is they're happiest when they're separated, right?
Okay.
Does that make sense? But if they're always moving around, are they always going to be able to maintain that separation? No, right? And that's kind of what we're saying, is that they're happiest when they can be farthest apart, right? Just like we're happiest when we have a lot of money, I don't know, whatever, or we have a lot of love, I don't know. My first thing that I go to is money. That's sad. Sorry, guys. Sorry. Was that right now? More to the middle? Sorry, I'm responding to the comments. Is that better?
Yeah.
Cool.
Thank you.
Yeah. So thinking about like the conditions under which we're the happiest, right? Are those always going to be the conditions under which we live?
No.
No, right? We strive for that, but it's impossible for that to always be the case, right? Because we live in a dynamic world, and that's just the way she goes, right? Same is true for electrons. Electrons are dynamic. They're always moving around. So even though they may be happiest in this one configuration, and they may strive to always have that separation, it doesn't mean that they always get it, right? So you can imagine that there's an extreme version of where these electrons are in motion and they end up being all on one side of an atom, right? Now again, this isn't something that will last, right? It's temporary. Because we know that this makes the electrons really uncomfortable, right? And then they're going to do what they can to minimize that uncomfortable situation. But when we have this kind of congregation of electrons, what we end up with is a separation of charges, right? So I have a net partial negative on this side of the atom, right? Which means that I have a net partial positive on the other side of the atom. Does that make sense? Cool. So, when we're talking about atoms or molecules coming into contact with each other, let's say we have our two, is that coming from my neighbor, the song of the laundry, or is that?
I thought it was mine. I didn't know whose it was.
I'm sorry.
No, that's,
My window. Oh, okay.
that's super funny. I was like, the laundry's done. Wait, I don't have that sound in my house. That was really fun. No, I love this. Honestly, like, this brings so much character to our interactions. I love it. Okay, so you can imagine that if you're bringing two atoms close together, right, that if you have these electrons naturally wanting to be separated out, right, that bringing them close together, what's going to happen to the electrons in this guy? So we've got electrons on this guy and electrons on this guy, right? How are they going to interact with each other as they come closer together?
They're going to be farther apart like the guy right above it?
Yeah, exactly, right? So these electrons here are going to be repelled by these electrons here, right? So as we bring these guys closer and closer together, what happens is, and I'm sorry, my molecules are getting smaller and smaller, right? We force the electrons in nearby atoms to repel away from each other, right? And when we do this, we actually set up a temporary dipole, right? Now, if these guys are repelling, then these guys, sorry, let me draw a better picture. I know, I'm sorry. When these guys are repelling, right, what you'll have is these guys, let's say, are running away from the electrons over here, right? When these guys run away from the electrons over here, right, this makes a partial negative charge on this side, right? That makes a partial positive charge on this side, right? Which is going to make the electrons on this guy line up over here to be attracted to that partial positive. Does that make sense? So then we get another partial negative over here, right? And another partial positive over here. And on to infinity. Does that make sense? So when we get these atoms or molecules closer and closer together, right, we can force the electrons to do this kind of separation, right? But it's not something that occurs naturally, right? It only occurs when we force it to occur, right? It can happen instantaneously, right? It can temporarily happen, but it's not something that would be lasting unless we're forcing it into that situation, right?
So on the exam, like, how would a question like this be asked? Would it show you like a Lewis structure and then it's like, what's the intermolecular force? Or like, how would you know that it's dispersion by looking at a Lewis structure? Because like, I get this.
Yeah.
This makes total sense. But
Yeah.
like, then I guess I'm just like
No.
confused.
That's a really great question. Okay, so when we look at a Lewis structure, how can we tell if we have a polar bond? A polar molecule, rather.
Asymmetry.
Asymmetry and polar bonds, right?
Bonds, yeah.
If you don't have those things, then you can't have a polar molecule. If you don't have a polar molecule, you cannot have dipole-dipole.
So then it has to be dispersion.
Exactly. So again, everything has dispersion forces, right? But if you don't have any dipole-dipole in your molecule, then you can't have anything but dispersion forces, right?
Got it.
So, when we're talking about phases, right, we started out talking about condensed phases. Condensed? I don't know how I just forgot how to spell that molecule, literally mid-sentence, whatever. Condensed phases, right? What we're talking about is solids and liquids, right? Condensed phases generally occur in molecules with dipole-dipole and or hydrogen bonding. Right? So if you have dipole-dipole or hydrogen bonding, right, then often the natural state that you find yourself in would be a liquid or a solid, right? For example, when we were talking about water, right? Water is a polar molecule, and we know that it's a liquid at room temperature, right?
Mm-hmm.
It's a liquid at room temperature because it likes to stick to itself, right? We call this property of sticking to yourself. Or something else. Whoa. Something else. Adhesion. Right? So I'm sure you guys have heard that term before, right? If you use an adhesive, it sticks something together, right? That idea of adhesion, right, is stickiness in molecules. And adhesion to itself gives you these liquid or solid states. You don't need to know this word necessarily, but it'll come up in subsequent chapters, so it's a good thing to understand. And I feel like most people already understand the idea of adhesion, at least loosely. You've heard it before, so. Does that make sense, guys? Cool. So if you have a disperse phase, aka a gas, right? Then you almost, I would say 90% of the time, don't have dipole or hydrogen bonding, right? You only have dispersion. Hence the name. Busted.
Did you see the question that Alex put?
So, hydrogen gas, this is a great question. Thank you, Alex. Thank you, Jessica and Alex. So hydrogen gas, right, is going to look like this, right? So are there any polar bonds there? No, right? So it can't be a polar molecule, which means the only intermolecular force that you can have is dispersion, right? And hydrogen is a gas, right? So these things make sense. In fact, if we're looking at our diatomics, right? We're thinking hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, right? This, oops, sorry guys. Right? The vast majority of these guys are going to be gases, right? How do we know whether or not something is a gas looking at our periodic table? Our periodic table doesn't tell us, but the one on the wall did. You guys remember the one on the wall in the classroom from like a million years ago? They're color coded, right? And you could look online for there. I'm sure that our periodic table, this guy, oh, it does tell you.
Yeah.
So you've got the solid, the liquid, and the gas, right? So in red, right, these guys are all gases. Same with hydrogen, right? So all of these guys are naturally gases, right? Now, as you go down the periodic table, what happens to the atoms? In the simplest kind of way.
They all become solids.
They do become solids, but why do you think that might be?
They lose
Or
electrons.
condensed.
So what happens to the atomic structure as you go down? Do they get bigger or smaller?
Oh yeah, they're bigger. Well, they're bigger.
They get bigger, right?
Yeah.
So as you go down the periodic table, they get bigger, right? As they get bigger, they have more electrons, right? And as they get bigger, their valence electrons are farther from the nucleus, right? So if you're farther away from the nucleus, then you're feeling less of that positively charged force holding on to you, right? So if you're feeling less pull, right, from your outermost electrons, then those electrons are basically more free to move around, right? If those electrons are more free to move around, then they can form condensed phases, right? Does that kind of make sense, guys?
Yeah.
So even though these guys still only have dispersion forces, right? They're still able to form condensed phases because the dispersion forces become more dominant as you increase in size, right? So bigger molecules will be forced to hang out closer together, right? And that forcing to hang out closer together makes the dispersion forces stronger. Does that make sense, guys? This is a great example. Yes. Thank you for bringing that up, Alex. So the smaller a molecule is, the more likely it is to be in a gas phase. because this dispersion doesn't really become a strong intermolecular force until you get much heavier. Right? And we can even think about it in terms of molar masses, right? So let's talk about the molar mass of, ooh, sorry guys, I got lag. Will it catch up? Maybe. You guys see what I'm writing, or is it frozen on your end too?